I'm Shunji from the RIKEN and working with Takemasa. And we are developing the global atmospheric data assimilation system named NICAM LTKF. And this study is the one to improve the precipitation forecast with our global data assimilation system. And let me speak about the background of our study. So currently, there are several satellites measuring the precipitation-related variables from the space, and many international space centers producing the precipitation field. And this is the one example from the JAXA. This is a precipitation map over the globe, and this is a space-sensed precipitation data. And we are calling this GSMaP. And we would like to improve the precipitation forecast using this kind of data. And our goal is to improve the numerical weather prediction using such a satellite-sensed precipitation data. And we also would like to produce a new precipitation product through our data assimilation system. And there has been a good pioneer study conducted by the Lin et al. And we know that the precipitation is one of the difficult variables to be assimilated. One reason is the bias between the observation and the model. And the other reason is the non-Gaussianity of its errors. And let's see their result. They conduct the precipitation assimilation experiment using GFS. And compared to this black line, this is a control experiment in their result. And if we assimilate the precipitation without any treatment, we generally have a degradation as shown in this green card. And they proposed a special treatment named Gaussian Transformation. With this transformation method, they got a large improvement as shown in the red colored line. So this study is conducted to conduct the two procedures to improve the precipitation forecast. One is the state estimation, as generally data estimation does. And second one is the parameter estimation. And I'm going to talk about this first part. And recently, we have a publication of this first part on the JGR atmospheres. So this slide briefly summarizes our experimental settings. So we use the NICAM model. This is a global atmospheric model and with 100 kilometer resolution. And for the data assimilation, we are using LTKF with 36 ensemble members. And localization and relaxation is written as here. And the key point is observations. We are simulating radio zone observations for control experiment. And in addition to the control experiment, we assimilate the GSMaP precipitation with Gaussian transformation. I'm going to explain. So here is an example of the precipitation field from the model in the left panel. And right panel is the observation. And gray color shows the missing data due to the unobservable area from the satellite. And as you see, the model tends to overproduce the precipitation, especially over the ocean. And this bias should be mitigated to assimilate the precipitation appropriately. And now here we are proposing the Gaussian transformation. And the concept of the Gaussian transformation is very simple. It assimilates the not precipitation variable directly, but assimilates the probability of the event based on the past precipitation record. So let's see an example. So for this method, we need to prepare the PDF of the precipitation for both model and observation. And once we have a forecast of observation, such as 1 millimeter per 6 hours, so we compute the CDF of this value. So here we can see the f of y is different because the model and observation have a different PDF of the precipitation. So here we have a probability of the event based on the past precipitation record. And now we could mitigate the bias problem in this procedure. And we have an additional procedure to mitigate the non-Gaussianity issue. We also prepare the PDF of the Gaussian distribution, and also we are preparing the CDF of the Gaussian Gaussian distribution. And what the Gaussian transformation do is to find the corresponding value of the CDF in the Gaussian transformation. So this correspondence is written in this equation, and based on this CDF value, we obtain the standard of deviation of the event based on the Gaussian distribution. So here, the y tilde and y tilde of the observation and model are different. Even if the observation and forecast is the same, we have a different standard deviation because they have a different precipitation record. So the key point is that how to produce this PDF of the precipitation. So we are proposing the flow-dependent construction of the PDF. So we conduct the spin-up experiment such as 30 days, And when it starts the experiment, we can obtain 30 days of the samples for precipitation. And based on these 30 days precipitation samples, we construct a PDF or CDF at each grid of the model and observation. Here is an example. So this black one is a CDF of the GSMaP precipitation, and red one is a model. And as you can see, the model really overproduces the precipitation relative to the observation. Based on this PDF, we can perform the Gaussian transformation, and we could do the data assimilation. For the second and third time steps, we can shift this sampling period, and as this way, we can obtain the flow-dependent PDF of the precipitation record. So let's see how the Gaussian transformation works. So this is the map I've already shown, and this is the one from the model and the observation. And the unit is a precipitation variable, such as millimeter per 6 hour. And by applying the Gaussian transformation, we can obtain this kind of map. So this is accounting for the probability of the event based on the past precipitation record. And as I mentioned, so for the model, we apply the Gaussian transformation based on the model CDF. And for the observation, we apply the Gaussian transformation based on the observational CDF. And as you can see, you may notice that there are several gray colors. It means a missing value. And our method transforms the precipitation based on the past precipitation record. Therefore, if there are no precipitation in the past 30 days, we cannot define the PDF. In this case, we cannot conduct the Gaussian transformation. But over the globe, we generally have a Gaussian transformed variables. And we check how benefit the Gaussian transformation is. So we check the O minus B statistics. And if the error is Gaussian, we expect that this O minus B statistics should follow the Gaussian distribution. And without Gaussian transformation, the O minus B histogram is largely different from the Gaussian distribution shown in the black line. But after the Gaussian transformation, this histogram is very close to the Gaussian distribution. And now we could expect the improvement by assimilating this kind of observation. We are also proposing the inverse transformation. In the last Gaussian transformation, we are transformed from the precipitation value into the standard deviation. But we could also the similar transformation from the standard deviation to the precipitational variable. So this is very important if we consider the bias of the model. So this is the map I've already shown. We conduct the Gaussian transformation based on the model CDF, and both of them represent the forecast. And when we conduct the inverse transformation based on the observational CDF, we can obtain this kind of map. Actually, this map is obtained from the model, but this map is very similar to the observation, like this. So this is the observed precipitation, and this is the forecast precipitation. And this transformation would be very useful to mitigate the bias of the model. And when we produce the precipitation product, we plan to use this Gaussian inverse transformation. So let's see the result. So now I'm going to talk about the data assimilation experiment. So this black and red line shows the root square difference against the era interim, and the lower value means the improvement. And as you see, after the spin-up experiment, we assimilate the GSMaP observation in addition to the radiozone observations, and we see the significant improvement. I don't talk here, but we notice that we need the thinning because satellite sense precipitation is really correlated, and that's why. So this means that we need thinning to assimilate the precipitation. Otherwise, we had a degradation. So this panel shows where we had an improvement by assimilating the precipitation, and U wind and V wind, and temperature and humidity. And for U, V, and T, So generally, this red color shows the improvement by assimilating the GSMaP, and we generally have an improvement in the southern hemisphere over the ocean, where the generally observation is relatively sparse. And for the humidity, we generally have an improvement. Actually, there are some degradation part, but we generally have improvement in Q2. So you also see the precipitation score with the different two threat scores. And here, we also improve the precipitation forecast. So now we can conclude that by assimilating precipitation with special treatment named Gaussian transformation, we could improve improve the state variable, and also we could improve the forecast. And I'm not going to talk about the second one, about the parameter estimation. So this is a panel showing our current global data assimilation system. We are simulating the conventional observation and MSA radiances. And we are also assimilating GSMaP precipitation with Gaussian transformation. And we are using NICAM, and we are cycling this process. And for these studies, we add one part for the parameter estimation. And so concept of the parameter estimation is that each ensemble have a different parameters. And based on this parameter and perturbation and observation, we estimate the parameter against the observation. And here, we would like to improve the precipitation forecast. Therefore, we used only the GSMaP precipitation to estimate the parameter. And this study estimates a globally constant parameter. That's why this estimation is mathematically equal to the ensemble transform Kalman filter. And what's important is we can estimate the parameter only together with the data assimilation cycle. So we estimate the parameter related to the one-lane parameterization as known as the Berry's parameterization. It controls how fast the cloud droplets is converted into the rain. And this parameterization can be written in this equation. And this B1 parameter is the one we would like to estimate. Again, this parameter controls how fast that cloud droplets is converted into the rain. And we have two special treatments to conduct the parameter estimation. One is maintenance of the ensemble spread. Unlike model variables, the ensemble spread never grows during the forecast, and we need to maintain the ensemble spread. And here we use relaxation to price spread with alpha equal 1. And second one is to avoid the excess of the parameter range. And using this hyperbolic tangent-based equations, we convert so actually the parameter estimation is conducted in this space. This is the one used for the ETKF and defined from the negative infinite to the positive infinite. And by applying these equations, we can obtain the parameters defined bounded by the range of the definition of the parameter. Actually, this B1 parameter is defined between the 0 to 1, and we would like to avoid the excess of the parameter range conducted by the ensemble Kalman filter. So this panel shows the time series of the mean and the spread of the estimated parameter. Left panel is the one used for the ensemble transform Kalman filter, and right panel is the one used for the forecast in the model. And the dot and the error bars show the mean and spread. And as you can see, due to the relaxation to price spread, we can keep maintain the spread of the parameter. And in the right panel, we see the rapid shrinkage of the parameter. And but actually in the data assimilation space, we maintain the spread. And this black one is used in the control experiment. And against this black line, the estimated parameter reduces rapidly. So let's see how precipitation field changes due to this parameter estimation. This panel compares the precipitation field from the control experiment without parameter estimation, and red one is with parameter estimation. And this is the one from the observation. And as you see, as I mentioned, the model tends to overproduce the precipitation over the ocean, and this overproduced area is remarkably improved by estimated parameter. As you see, this white colored region is very large compared to the control experiment. And we validated the forecast scores. So black and red color shows the running mean of the 6-hour precipitation forecast from the control and test. And this overproduced problem from the control is significantly improved by parameter estimation, and the threat score is also improved. We have also validated the atmospheric variables for temperature and humidity. And we are comparing the absolute value between the test and control against the error interval. And basically, the red color shows the improvement. For the temperature, we see the black, blue, and red color. It means the improvement and degradation areas both are observed. But the Q, we generally have improvement especially in the lower troposphere in the tropics. And it is very reasonable to see the improvement in the Q because Q is a very close variable to the precipitation. Okay, I'm running out and I'd like to summarize. So these studies, we propose two procedures to use the precipitation data efficiently. So one is the state estimation, and the Gaussian transformation works well with our system, and analysis and forecast was improved. And second part I present is the parameter estimation, and we did improve the precipitation forecast, and also dry bias in the lower troposphere was improved. That's all I have to say. Thank you very much for your attention.